All right, atomic theory 1, here's the topics that we'll cover. So pure samples and mixtures. Pure sample contains particles, unit of one specific atom or molecule. Mixtures contain particles or units of more than one specific atom or molecule. So the history of atomic theory, Democritus, he was the first to theorize that all matter was made of very small, indivisible particles that he called atomos. So he was the first to claim that. Then Lavoisier came along, and he carefully weighed the reactants and products in various chemical reactions and found that mass is neither created or destroyed in a chemical reaction. So he verified the law of conservation of mass. He also gave oxygen its name and showed how it's involved in combustion reactions. But he was actually a tax collector for the government, so they executed him on the guillotine. Joseph Proust, he came up with the law of definite proportions, which states that different pure samples of the same compound always contain the same proportions of each element by mass. So water is always going to be 88.8% oxygen and 11.2% hydrogen by mass. So if you take 16, which is the weight of oxygen, and divide it by the water times 100, you'll always get the 88.8%, and same thing with hydrogen. So then Dalton, he kind of threw it all together, and he figured that if elements were made of tiny indivisible particles, then like compounds would contain equal numbers of each type of element. So each element in a given compound accounts for a consistent percentage of that compound's mass. And so in 1808, he published a system of chemical philosophy, and it just kind of outlined his theories, and these are his 4 postulates or theories. So his first hypothesis or postulate he kind of took from Democritus, right? His second hypothesis was his own, but it's not completely correct, right? All atoms of a given element are identical, and all atoms of different elements are different. Well, they're not all identical, are they? We have got isotopes, they have different number of neutrons, we have ions, different number of electrons. So that one's not quite right. The third one is similar to Lavoisier's law of conservation of mass. Atoms are made of mass, so they can't be created or destroyed, but they can be converted to energy like in nuclear reactions. So, and then the fourth hypothesis is kind of an extension of Proust's law of definite proportions. Elements in a given compound are always in the same proportions by mass because the atoms of each element in a given compound are in the same proportion by number. So the ratio of one type of atom to another type of atom in a compound is always constant. There's always 2 hydrogen atoms and 1 oxygen atom in a water molecule. So Dalton didn't really know what the shape was, right? But he postulated that elements were composed of these tiny indivisible particles called atoms. So atoms of different elements always combine with one another in the same whole number ratio when forming a certain compound. This explains why the ratio of the masses of the constituent elements in a given compound is always identical. And we're going to kind of look at average atomic mass later. Here we have J.J. Thomson, and he conducted a series of experiments with cathode ray tubes. So tubes have had most of the air sucked out of them like a vacuum and are hooked up to a source of electricity. It was known that a stream of particles flowed through a cathode ray tube when it was hooked up to electricity. And they knew that a stream contained particles because they had set up paddles, and they would spin when their fins contacted that stream. So Thomson set up this electrical field around the cathode ray tube. He observed that particles flowed towards the positive side and away from the negative side. And he concluded that the particles carried a negative charge. So with this, he discovered what was later known as electron by measuring the degree of deflection in the series of similar experiments that he was able to calculate the charge to mass ratio of an electron, which is 1.76 times 10 to the 8 coulombs per gram. You don't really need to know that. Just like a fun fact. Okay, then we've got Rutherford, and he, before he did his gold foil experiment, he did this one where he placed radioactive material inside a lead casing so that the particles it emitted shot through a magnetic field. All the particles emitted collided with this fluorescent screen, and this allowed him to see where they ended up. So he noticed that the particles, the beta particle, were curved toward the positive end of the electric charge, and so it carries a negative charge. The alpha particle curved toward the negative plate, meaning it was positive, which we know is a helium nucleus, right? The gamma ray didn't curve in either direction, so they just assumed it's a neutral particle. They didn't know it was, energy. So from this experiment with Rutherford and Thomson, it was known that, okay, atoms are made up of positive, negative, and neutral particles. It's also known that atoms were neutral themselves, but they didn't really know how it was put together. So then in this experiment, this famous gold foil experiment, he kind of figured out how they were put together. So he loaded a lead block full of radioactive material that emitted alpha particles, just alpha particles. And these were shot at a thin sheet of gold foil that was surrounded by this circular fluorescent screen. Now the vast majority of the particles traveled straight through the gold foil. 1 out of every 8,000 was deflected at some random angle, and 1 in every 20,000 was deflected at an angle greater than 90 degrees. So from this, Rutherford concluded that an atom is mostly empty space with a small positively charged core. He compared the nucleus of an atom to like a grape hanging in the center of a cathedral, and said that, like, okay, electrons or pieces of dust circulating around it from as far away as the outer walls of the cathedral. Most alpha particles that just straight through. 1 out of every 8,000 was deflected. So if this picture was drawn to scale, the nuclei would be much further apart. But you get the gist. If the alpha particle kind of nicks the nucleus, it would deflect and bounce back at this. And if it makes a direct hit, it bounces straight back. So his conclusions were the nucleus small, dense, and positively charged. So negatively charged electrons, they occupy the vast majority of the volume's atom, while the core, we'll get to that in a second. Okay, so we have these subatomic particles. Protons and electrons have equal but opposite charges. A neutral atom has equal number of protons and electrons. Protons and neutrons have equal masses. They're a little bit different, but for the most part the same. The mass of an electron is much, much less. So for this reason, the mass of electrons is rarely taken into account. Most of the mass is found in the nucleus of the atom. So this top number, just convention, how we write it, is going to be your mass number. The bottom number is your atomic number. Your mass number is equal to the number of protons plus the number of neutrons. And then your atomic number is always your protons. And if it's a neutral atom, then also the number of electrons. Okay, so we abbreviate these with A and Z. Mass number is A, which you would think it's atomic number, and I always get these confused because I always think A should be atomic number, but that's neither here nor there. Okay, so this atom would have 6 protons, 6 neutrons, 6 electrons, right? Because 6 plus 6, 12. How about this? How many protons does this atom have? How many neutrons? How many electrons? 6 protons, 8 neutrons, 6 electrons. Again, how many do you think each would have? 1 proton, no neutrons, 1 electron. So really, hydrogen is just a proton, and so anytime we talk about a hydrogen, we usually just call it a proton. This guy, he is going to have a neutron, though. All right, so isotopes. So that one, H2 here, these are isotopes, and it's found in what we call heavy water. They call it heavy water because the isotopes increase the overall mass of the water molecules. The nucleons in all atoms other than carbon-12 are not exactly 1 AMU, but this is the scale that we measure atomic masses with. So average atomic mass is the mass on the periodic table. It's an average of the percentages of the ratios of the isotopes for each given element. Mass spec. So in the mass spec, atoms from a pure sample are passed through a beam of high-speed electrons. And the high-speed electrons remove electrons from the atoms, and they convert them into ions. So the positive ions are accelerated as they pass through the electric field. And these positive ions are deflected toward the negative plate as they pass through the magnetic field. And this can be explained through Newton's F equals ma. We're not going to get into that, though. The isotope with the greater mass experiences a smaller acceleration towards the negative plate. And the distance between the locations where the ions strike the detector plate are proportional to the mass of the ion. So the number of ions that strike the detector plate is then counted, and then that data is used to determine percent abundance of each isotope. So that's where this data comes from. They've ran they took some silver and they ran it through mass spec and they get this data. So from this data, we want to find the mass of silver. So first, this is our equation. You're going to take the mass, the mass of the first times the percentage plus the mass of the second times the percentage, and however many, and then it's just algebra from there. Okay. So here, use the mass spec data below to find the average atomic mass of the element in question and identify the element. So these are the numbers of matter. This is the mass number. So this is your percentage of this mass. So I think I have the equation later, but it's just mass of your first times whatever percentage. And don't forget to move your decimal place. Plus the mass of your second one times the percentage. And then however many you have, you would add them up. So then this one, the mass of the first, the mass of the first element, here's your percentage, plus the mass of the second one times its percentage. And then it's just algebra, solve. Oops, there go my arrows. So this would be chlorine. And that checks out, that's the mass on the periodic table. Formula and molecular weights. So a formula unit really is basically an ionic compound because they exist in networks like lattice structures. So NaCl is a network where many sodium and chloride ions are stuck together in a 1-to-1 ratio. We don't have molecules of sodium chloride, and so we refer to that as a formula unit within the network solid. And we find the weight or mass of one formula unit. So to find the formula weight, we know there's in magnesium hydroxide, there's one magnesium, and then this little 2 distributes to what's ever inside the parentheses. So we've got 2 oxygen and 2 hydrogen. So you'll just take the number of particles times its mass to get a total mass for each element that you have, and then add them all up, and that's your formula weight. And here is that equation. Now this formula isn't given on the AP exam. It's just the procedure to find the percent composition of anything. So sometimes we'll call it mass percent. From pre-AP, we called it percent composition. And you'll notice that we've got lots of names for the same thing. And that's one of the tricks that y'all need to kind of pay attention to. Okay, so mass percent of water. We have 2 hydrogen atoms. Times its mass divided by the total. So this is total water. This is oxygen, and then we've got 2 hydrogen. 11.2% hydrogen. Same thing, the total number of your oxygen divided by the total weight of the compound, 88%. And then check, you add them up, and they should equal 100 or be really, really, really close. All right, so try this one. Pause the video, try this one, see if you can get it. Okay, history of atomic theory. So John Dalton came up with the law of multiple proportions. When 2 elements form more than one compound, the different masses of element A that combine with a fixed mass of element B can always be expressed in a small whole number ratio. The small whole number ratio tells us how many times more A is contained in the more massive compound. But it has to be a whole number because compounds can only be made of whole numbers. So if we look at water or hydrogen peroxide, you take your ratio of your peroxide and the ratio of your water, and you get 2. That means peroxide has twice as many oxygen atoms as water. It also works when we use mass percent values. So Y'all need to be able to do this for the AP test, and we'll practice this. Mass ratio of elements in a pure sample. If any nuclear decay of an isotope occurred, the sample would no longer be as pure as it would contain foreign elements or compounds. Okay, so y'all need to try these problems on your own. We're going to check them in class.